Today we're going to start talking about polynomial functions and their graphs. We have already studied the concepts and applications of two kinds of polynomial functions. Linear functions and quadratic functions are both subsets of a larger class of functions called polynomial functions. So linear functions are degree 1 because the highest exponent that you see on x is a 1. You actually see it because we don't really write x to the first because x to the first is just x, right? Quadratic functions we call degree 2 because the highest power on x is a 2. But polynomials can have degrees higher than that, 3, 4, 5, etc. Okay. So this is the official definition of a polynomial function. And I wish I didn't have to write it down because the notation of trying to describe what this thing is really overwhelming with all these subscripts and dots, and it's the A's. If you just ignore the subscripts, the A's are coefficients. They're just numbers. And then the exponents will start at some value n. Like if n were 5, it would go 5, 4, 3, 2, 1, 0. So your exponents start at some value, and then you write them in descending order. And the A's are just numbers. So let's come up with some examples here. So I want a degree 5 polynomial. That means the highest degree of x is going to be a 5. It's going to have 3 terms, so 3 pieces to it that I add or subtract. A leading coefficient of -3. So the leading coefficient is the coefficient in front of the highest power of x. And the quadratic term, that would be the x squared term, has a coefficient of √2. All right, so we're going to start, we'll call it p of x for polynomial function, right? And it's degree 5, which means the highest power of x is an x to the 5th. So I'm going to put my first term is going to be something x to the 5th. Yep, and the leading coefficient is what goes with the highest power of x, and that's a -3. So that's one of my 3 terms. Okay, I have a quadratic term, so I'll put plus. Quadratic term is an x squared term. And the coefficient on the quadratic term is a √2, so I put a √2 in front. And then I just need one more term because I'm supposed to have 3, but they didn't tell me anything about the third term. So I can just make one up. I could write plus x or minus 7x or plus 2, anything I want. So I could do plus 18 for my third term. Right, because you got it, yeah. You don't have to have every single power of x shown, yeah. Because technically there is an x to the 4th term in here. It's just 0 times x to the 4th. And so the coefficient is 0, and we don't write it because it just drops out. All right, a polynomial function with degree 0. So the degree is the highest power on x. So if my highest power on x is 0, I have 1, yeah. So it could be like p of x, right, equals 5. I just picked a leading coefficient of 5. 5x to the 0, which is just 5. 5 times 1, because anything to the 0 is 1. So a constant term, another way of classifying a function that's constant is as a polynomial that has degree 0. All right, a function that's not a polynomial. So polynomials have to have positive integer coefficient exponents on the x's. So like x to the -2 would not be a polynomial. Yep. Because the exponent is negative. Square root of x would not be a polynomial because its exponent is a fraction, right? X to the 1/2. So polynomials can only have exponents that are positive whole numbers. All right, this scatter plot shows the consumption of natural gas in quadrillion BTUs. So I guess it doesn't, I don't even have any sense of how big that unit is. So I guess we're just trying to get an idea of the ups and downs here, so the units don't matter that much. So we're measuring in quadrillion BTUs by the United States in the decades from 1960 to 2000. So our consumption of natural gas has varied from pretty low to high to low to high. So what does this graph tell us about our consumption of natural gas over the decades from 1960 to 2000? %200 over how long? Okay, so if you just look at the two endpoints, it grew a lot, right? It 200%. Well, it doubled. That's a growth of what percent? 100% growth it corresponds to doubling. Yeah. All right, but is there more to the story than the fact that it doubled over 40 years? Yeah, there's a dip. It spikes and it dips and it spikes again. Okay. So let's write that down. Let's say, well, it doubles from 1960 to 2000. We'll say, but it dipped. It spiked and dipped in between. So would a linear or a quadratic function be a good choice to model this data? Would either of them capture that spike and dip? No, because if I tried to do a line, I'd get something like that, which wouldn't be a bad fit, right? But it doesn't capture the fact that we went up and down and up again. Or if I tried to do a quadratic, it would maybe look something like that. And then then that would show it going back down when it doesn't really do that, right? So neither of these would be good. So instead, I want you to try to fit a curve to these things, to these 4, 5 points. Try to fit a curve that's smooth, can't have any sharp corners, and continuous. You have to be able to draw it without picking up your pencil. And try to draw a curve that kind of follows that pattern of spike, dip, and back up. Nice. Basically, we're just trying to connect the dots with a smooth, continuous curve. So I do the best I can, and I kind of go something like that. So I want to compare this graph that I just drew to the graph of a polynomial function that is the best model for this data. Okay, so I have it on the board here. You don't have it at your seats. It's up here. It's just up here. Does that look similar to what you drew? Yeah. This is the formula for that curve. It's a polynomial. What is its degree? 3. The highest power on x is a 3. So let's see, they asked me what the degree was. What is the degree? 3. Good. So we can use polynomials that have a higher degree to capture trends in data that we cannot capture with a line or a quadratic. All right, so here's another example. The number of AIDS cases diagnosed in the United States X years after 1983 are displayed in this scatter plot. It's difficult to find a model that's useful over long periods of time, and this is true in general, right? It's difficult to find a model that can be used to make predictions long into the future. Okay, so here's a cubic, I fit a cubic function to this data. right? A negative 49x cubed, blah, blah, blah. It is a really good model for the data between 1983 and 1991. But after 1991, now it's a terrible model, right? It will make absolutely terrible predictions. So here to here, my points were all pretty closely on that curve, but afterwards, that model no longer has any predictive value. Okay. So by year 21, which is 2004, it would predict that there are negative numbers of AIDS cases diagnosed. And that just doesn't make any sense, right? So the far right end behavior of the graph makes it inappropriate for modeling AIDS cases into the future, right? Because you can't have a negative number of cases. So I have this arrow to indicate that this just keeps going down forever. We'll just keep getting more and more negative. So this is a case of model breakdown. Model is giving us nonsensical predictions. So we use this language and notation to describe this far end behavior to the right, that it just keeps going down and down and down and down forever. We say as x approaches infinity, so you read that arrow as approaches. As x approaches infinity, f of x approaches negative infinity. So as your x's head out to the right, as your x's get really, really big, in this case, as time moves forward, right? After year 21, 22, 23, 24, as the years keep going on and on and on, this curve predicts that the number of AIDS cases will just get more and more and more and more and more and more negative. So we say as x goes to infinity, or as time goes to infinity, the number of AIDS cases goes to negative infinity. Doesn't make any sense, but that's the notation we use to describe it. So the behavior of the graph of a function to the far left or the far right is called its end behavior. What happens at the ends, far right and the far left. So the graphs of all polynomial functions will eventually rise or fall without bound as you move to the far right and the far left. It will either go up or down forever. So how can we tell what the graph of a polynomial function will do as we move toward each end? So let's look at a few polynomial functions and see if we can figure this out. So we have linear functions, right? That means the degree is 1. And we have rising to the right, falling to the left, or rising to the left, falling to the right, right? So I just wrote down what the description of this is. This says as x goes to negative infinity, so as my x's go to the left, the y values go down. So I have negative infinity, negative infinity. And this sentence underneath it says that as x moves to the right, my y values go up. So positive infinity, positive infinity. So now look at this line. It has negative slope. As x goes to negative infinity, as the x values head this way, what's happening to the y values of the graph? Where are they headed? Positive infinity. And as my x values go to the right, as my x's approach positive infinity, where are my y's going? Negative infinity. Good. All right, fill out the rest of the end behaviors that aren't shown there. All right, for these quadratics, these parabolas over here on the right, they have degree 2, which is even, right? 2 is an even number. The first ones we did were linear functions, would have degree 1, which means they're odd. Degree is odd. And here degree is even. And as x approaches negative infinity, f of x approaches infinity. And as x approaches positive infinity, f of x approaches infinity. So for this graph on the left, both ends, the right and the left, go up. And now here on the right, both ends, the far left and the far right, both head down to negative infinity. So these should both be negative infinities. All right, so now we're going to look at cubic functions that have degree 3. So another set of functions where the degree is odd. We've got 1 and we've got 3 here. So let's see, as x, this one's filled in. Look at this one. As x goes to the left, when you look to the far left of the graph, what are the y values doing? They go to positive infinity. And we look to the far right of the graph, where do my y values go? Negative infinity. Good. All right, and now some quartic functions, some polynomials that have degree 4. So in this case, that's even, right? 4 is an even number, so I have even degree polynomials now. The one on the right, the one on the left, the far right and the far left both go up. So these are both positive infinities. And the one on the right, both the far left of the graph and the far right of the graph go down. So these are both negative infinities. All right, so what do you notice about the end behavior at the far right and the far left for odd degree polynomials? That, yeah, that one goes up and one goes down. So they have opposite end behavior. One will head up and the other will head down. Which is which, we don't know yet, but one goes up, one goes down. And even degree polynomial functions, what do you notice about their end behavior at the far right and the far left? They're the same. They either both go up or they both go down. So they have the same behavior at each end. So odd degree, opposite behavior, even degree, same behavior at each end. All right, and then we can look at the leading coefficient to tell us about whether they both go up or they both go down, or which arm is up for an odd degree. So as x increases or decreases, a polynomial function will either will eventually rise or fall. So there's two cases. If n is odd, you have this opposite behavior, right? And one arm's up and one arm's down. The way you can tell which arm is up has to do with the leading coefficient. So the very first number in front of the highest power of x, if that number is positive, you get a right arm up, left arm down, right? Like this. And if that number is negative, that leading coefficient is negative, then it switches. You get a left arm up, right arm down. Right? Because think of that if you put a negative out front of a function, it's going to flip it over the x-axis. So if I flip this guy over the x-axis, the end behavior changes. And then when n is even, okay, we either get both arms up or both arms down. You get both arms up if the leading coefficient is positive, and both arms down if the leading coefficient is negative. So let's take a return to this function that was modeling the number of AIDS cases. We use this cubic model to model the number of AIDS cases diagnosed between 1983 to 2008. We want to use the end behavior to determine why this model is not appropriate in the long run. Okay. So what is the sign of the, this is poorly worded, what is the sign of the leading coefficient? Negative, right? It's negative 49 is the leading coefficient. What is the degree of the polynomial? 3, good. All right, so I have a negative leading coefficient and a odd degree polynomial, which means does my function have same end behavior or opposite end behavior? Opposite, because it's odd degree. And so what is the end behavior of this graph over time as we move to the far right? It's negative. Yeah. Because of the negative leading coefficient? Yeah, if you think of it like a line that has negative slope, that would fall left to right. Yeah. Yep. So my leading coefficient's at negative 49. It's negative, so that means that the right arm goes down. So there's the left end, right? And the right end. So left and right. Left and right. And I can describe it as to the far right. I can describe that as x approaching positive infinity.
Right, so we're talking about it moving to the right.
Yeah. Yep. So the end behavior as we go towards the right, I want to know what's happening to the y values. They're going down, right? Negative leading coefficient with a odd degree. It has end behavior that looks like that. And I left the middle blank because we don't know anything about what happens in the middle. We just know what happens at the ends. So that's going to go down to negative infinity. So as x approaches infinity, the polynomial, which was f of x approaches negative infinity. So that makes it a bad model because we can't have a negative number of AIDS cases. So the end behavior makes this a bad model for long-term predictions, right? It could be a good model for small amounts of time, bad model in the long run. All right, so values of x for which f of x equals 0 are called the zeros of the function. And where do real zeros appear on the graph of f? X-intercepts, yeah. Places where the function equals 0 is how you find x-intercepts. So I want to find all the real zeros of x cubed minus x squared minus 2x. So to find real zeros, that's the same thing as asking you to find x-intercepts. So I would take my function, replace the f of x or the y with a 0. And I want to solve it for x. You have any ideas on how to solve this guy? Pull out an x, yeah. Can factor out an x. So I have x squared minus x minus 2. Then what? Yeah, set each factor to 0. So either x equals 0 or x squared minus x minus 2 equals 0. And does x squared minus x minus 2 factor? I think it does. X minus 2, x plus 1. So since it factored, I can set each factor equal to 0. So x equals 2 or x equals negative 1. Or 0, yeah, from over here. Yeah. Okay, so my real zeros are x equals negative 1, 0, and 2. You can write them in any order. I went smallest to biggest because I'm just nerdy like that. Did you have a question, Sabine?
Whatever, I was thinking, we're not plugging in
Right. If I plugged in 0 for x, what would I be finding? I'd be finding y-intercepts. Yeah, good. All right, so if these are my zeros, the corresponding x-intercepts, I would write them as points. So this would be negative 1, 0, 0, 0, and 2, 0. Right, x-intercepts are points on the x-axis, which means the y-coordinate is 0. Okay, let's use our graphing calculator to verify that I have these 3 x-intercepts. So I'm going to put in this original function right here. X cubed minus x squared minus 2x. I'll just use a standard Windows Zoom 6. Does it look like that graph has x-intercepts of -1, 0, and 2? It does. Yeah, so we got it. All right, let's examine the behavior of the graph near the real zeros. X equals 1 for each of these polynomial functions. So both of these functions, we have x minus 1 squared and x minus 1 cubed. They both have a 0 at x equals 1, right? If I were to set each of them equal to 0 and solve, we would have a 0 at x equals 1. That is an x-intercept. And both of these graphs have x-intercepts at x equals 1. Now, what's different about the way this x-intercept looks versus this x-intercept? Yeah, the first one's a relative minimum, and the other one goes through. Yeah. So the first one, it like bounces off the x-axis. It like comes down and touches it and turns back around. And this one goes right through the x-axis. So for this one on the left, the reason we have the bounce off x-intercept is because the factor x minus 1 occurred twice, right? Because x minus 1 squared means x minus 1 times x minus 1. So that means that 1 is a 0 of multiplicity 2. That's just the wording we use to say 1 is a 0, but it happened twice, right? Because when I was solving this, I would have this equals 0, set each factor to 0, and you would get x equals 1, x equals 1. Right? So if you get x equals 1 as a 0 twice, we say it's a real 0 with multiplicity 2. Over here for g of x minus 1 is a factor 3 times. X minus 1 cubed means x minus 1 times x minus 1 times x minus 1. And if I was solving for the zeros, I would get x equals 1, 1, and 1. Set each factor to 0, so I get x equals 1 as a factor 3 times. X equals 1 is a 0 3 times. So that means that 1 is a 0 that has multiplicity 3. So the multiplicity of a real 0 tells us about the graph's behavior near the x-intercept. If the multiplicity is even, then the graph touches the x-axis and then turns around. And if the multiplicity is odd, the graph crosses through the x-axis at the real 0. So just to keep in mind, if you want to determine the multiplicity of a 0, you have to be able to write your function in factored form to see if any factors repeat. All right, I want you to look at number 10 in your groups here and discuss. We have two graphs of polynomial functions. Find the zeros, state whether the multiplicity of each 0 is even or odd. All right, so looking at these graphs in number 10, just the first one. What are my real zeros? Where are they? -2, 0, and 3. My x-intercepts. In all three of those x-intercepts, does the graph bounce off the x-axis, hit the x-axis and turn around, or go through the x-axis? It goes through, which means what kind of multiplicity do I have? Odd. The multiplicity of my 0 has to be odd. Now, I can't get any more specific than that by looking at a graph, right? So I know that it's, 1, 3, 5, etc. would be the number of times that 0 occurred when I was trying to solve for the zeros. But I can't be more specific from looking at a graph. If I had an equation, I could tell you the exact multiplicity, but I don't. I just have the graph. So a possible equation for this function, let's see. So I have some polynomial function, and I'm trying to find its zeros. right? I don't know what this function is, but I would factor it, right? If I could, I would factor it, and I would say, okay, well, I got 3 factors equal to 0, and then I set each one to 0. Okay. And what I got as zeros when I solved each of these was -2, 0, and 3. Okay, so if I had an equation, something equals 0, and I solved and got x equals -2, what had to be in this parentheses? X plus 2, right? How about here? If I solved and got x equals 0, what was in the parentheses? X, yeah. And if I solved and got x equals 3, what was in the parentheses? X minus 3. Okay. So that means my 3 factors are x plus 2, x, and x minus 3. Then all you have to decide is what exponents go on these guys. And you can guess at that based on the multiplicity. We know that all of those exponents have to be odd because each of the multiplicities were odd. So the simplest equation to write would be to make them ones. So I think I'm going to do that, but it doesn't mean that they're ones. They could be 1, 3, 5. Several of you wrote down other things. So there's this leading coefficient out here that I don't know, A. We'll learn how to get that later. But for now, we can start by doing x minus 0 to the first and x minus 3 to the first. We can start just by getting the factors. All right, looking at the next graph, where are my zeros? In fact, there are 4 of them, so I should have given you another space here. Yep. -3, -1, 1, and 3. Those are my x-intercepts, which means those are my real zeros of the function. All right, -3. Does it cross or bounce off of the x-axis? Bounces off, which means that the multiplicity is even. Yeah. At -1, do I cross or bounce off? Cross, which means that the multiplicity is odd. And at 1, I bounce off. Multiplicity is even. And at 3, I go right through, which means my multiplicity is odd. All right, so if I have zeros, if I have a 0 of -3, what do I have to have as a factor? +3 is a factor? Be more specific, please. No, I mean factor. So if I were to factor this equation so that it was 4 things multiplied together, x plus 3 has to be one of my factors. If x equals 3 is x equals -3 is a 0, x plus 3 had to be a factor. All right, and if x equals -1 is a 0, what had to be a factor? X plus 1. And if x equals 1 is a 0, as a factor, I had to have x minus 1. And if x equals 3, I had to have x minus 3. And then the question is, what are my exponents? Okay, so well, I know on the negative for the x plus 3 factor, the exponent has to be even. So the simplest thing to make it would be 2. X plus 1 has to be odd, so I'll make it 1. X minus 1 has to be even, I'll make it 2. X minus 3 has to be odd, I'll make it 1. I could. I don't really know what the exponents are. All I know is if they're even, is that they're even or odd. So I could have done 4, that's even. I could have put a 3 here because that's odd. 2, even. 1, odd. Mm-hmm. No, I don't think so. Doesn't matter. That's, yeah, personal preference. Yep.
The whole kind of like possible equation, just trying to wrap up. What supposed to be, what the graph would look like.
Yes. Yeah, so it's just a possible equation. Yeah, so we're saying, okay, if this is our picture, right, this is our graph, we know the zeros, which means we know some factors, and we know something about the factors in terms of how many times they occurred, right? So the reason I'm saying a possible is because I don't really know what the multiplicities are. I just know if they're even or odd. And I don't know this leading coefficient A, which tells you that's a vertical stretch or compression factor. Because if I were to stretch this whole graph, its zeros would stay in the same place and they would have the same multiplicities. So I don't know what the A value is, and I don't know exactly what the multiplicities are. So I'm just trying to like make a connection between what this graph looks like and what its equation must have looked like in general without knowing everything about it. So this would be plus 3 squared plus 1 to the first minus 1 squared and minus 3 to the first. All right, so this time I've given you the full equation, right? You know what all the you know what all the powers are. You know the leading coefficient. I want to find all the zeros and give their multiplicities. State whether the graph crosses the x-axis or touches the x-axis at that zero. And then we'll talk a little bit more about trying to visualize what the graph looks like. All right, so to find the zeros of f, you set f of x equal to 0. So I would set 1/9 times x plus 3 squared times x plus 1 times x minus 1 squared times x minus 3 equal to 0. And to solve that thing, first I might multiply both sides by 9 or divide both sides by a 9th, because then I can just get rid of that leading factor. And it would just be gone. And when you multiply both sides by 9, the right side would be 0 times 9, and it would stay 0. So then we set each factor equal to 0 and solve for x. So I set x plus 3 squared equal to 0. Actually, I'm going to write each one out. X plus 3 squared means x plus 3 times x plus 3, right? So I've got x plus 3 equals 0, x plus 3 equals 0, x plus 1 equals 0, x minus 1 equals 0, and that happens twice because that's an x minus 1 squared. And x minus 3 equals 0. So I took each factor, set it equal to 0, solve them, and I get x equals -3, x equals -3, x equals -1, x equals 1, x equals 1, and x equals 3. All right, so my zeros are, what's my first 0? -3. How many times is that a 0? Twice, so that means it has multiplicity 2. Okay. Next 0 is x equals -1. How many times did I get that as a 0? Once. X equals 1. How many times did I get that as a 0? Twice. And x equals 3. What's its multiplicity? 1. All right, so we're going to try to begin to visualize what the graph of this thing looks like. And part of knowing what its graph looks like is thinking about its end behavior. But to think about its end behavior, we need to know its degree. What is the degree of this polynomial? Yeah, can you explain how it's 6? Mm-hmm. Yeah, so this is in factored form. But if this had been all multiplied together, right? If I did x plus 3 squared, I would get x squared plus 6x plus 9, right? And then I would multiply that by x plus 1. And now I'm starting to have to do a lot of work, right? A lot of distributing. Then whenever I get that, I'm going to multiply that by an x minus 1, and then by x minus 1 again, and then by x minus 3. And there's a ton of multiplication if I want to multiply this all out. But I don't have to do all of the multiplication if I only want the leading term. I only want the highest power of x, right? So this would be x plus 3 squared. My highest power of x would be an x squared times an x squared times another x. Just think about the highest power of x in each factor and then multiply them together and you would get x to the 6th, your highest power of x, if you were to do all of that distribution, which I'm not going to make you do. You just have to think about, if you were to do it, what would the highest power of x be? Yep. It is not. It is not a coincidence that when I added up these multiplicities, 2, 3, 5, 6, I got the degree. Because that's how many factors I had, right? X plus 3, that's 2, 3, 5, 2, 3, 4, 5, 6. 6 factors, degree 6, 6 zeros, including the multiplicities. So the degree is 6, right? So I know the end behavior should be both up or both down because it's an even degree. What is it about the 1/9 that's important? Positive, yeah. So since it's positive, I have both arms up. So I can start to try to maybe draw a little mental picture of this thing. I guess I'll do a new page. And I know I've got zeros at -3, -1, 1, and 3. -3, -1, 1, and 3. And -3 has multiplicity 2, which means it bounces off, and my end behavior is both arms up, right? So this would have to kind of go like this, bounce off there, and there's my end behavior that bounces up. Okay, and then at -1, the multiplicity is 1, so that's odd, it has to go through. So this must turn around and come back down here. And then what's the multiplicity at 1? Even, it's 2, it's even, so it has to bounce off of that one. And then it comes back and goes through that one and goes up. I mean, this is a very rough sketch. We don't know how low they go, stuff like that. Yeah. Yeah. So we have a very rough sketch. We could use our graphing calculator to be more accurate, or we could make a little table of x, y's to try to be more accurate. But we have a good mental picture of what this thing looks like without having to do that much in terms of calculation. So the sign and the leading coefficient tell me that the end behavior looks like this. Both arms up. Yeah. Yes, I do also want you to be able to describe end behavior using this notation. And as x approaches -infinity, f of x approaches infinity. All right, we have reached a turning point. All right, so what is the degree of this function, do you think? 3, yeah, because I gave you the formula, right? And the highest power on x is a 3. Okay. How many real zeros does that function have? 3. 3x intercepts. Do you think that's a coincidence? Nope. Degree and the number of zeros being the same, not a coincidence. How many turning points, that is local maximums or minimums, 2. Okay. What happens at each turning point? Changes direction. It goes from increasing to decreasing or decreasing to increasing. Increasing to decreasing or vice versa. All right, so our conjecture about the degree and the number of zeros being the same is almost right. It's not always the same, okay? It turns out that if a polynomial has degree n, then it can have at most n zeros. It might have fewer, right? So think about the graph of x squared. Or x cubed, right? How many real zeros does it have? 1. So it doesn't necessarily have 3. We can even be more specific. Like, what if I said the graph of x cubed plus 1, right? That's x cubed shifted up 1, and it looks like that. It has 1 real zero. All right, so it's possible to have fewer real zeros than the degree, but no more. Yeah. And then how, in this example, is the degree related to the number of turning points? 1 fewer. The number of turning points is 1 fewer than the degree. And it turns out that that is almost a good conjecture, right? Because if we have degree n, then f has at most n minus 1 turning points. It could have n minus 1 like it does in this example. But think about x cubed. How many turning points does x cubed have? None. Yeah. It never switches from increasing to decreasing, or it just stalls. Yeah. Right. So we have an x cubed that has no turning points, right? So the most turning points it can have is n minus 1. Cubic, the most it could have is 2. Yeah. All right. So what do I have to tell you? Do your homework. That's it.